Welcome to the Deep Dive. We're your shortcut to being well-informed, mixing surprising facts with, hopefully, just enough humor to keep you listening.
That's the plan.
Today, we're diving deep into the periodic table. And I know what you might be thinking, high school chemistry charts, right?
Right, rows and columns. Very static.
Exactly. But we're going beyond that. We're looking at the hidden stories, the surprising personalities of the elements, and how they shape literally everything. From the stars down to, well, us. I remember as a kid, I was sick a fair bit, and sometimes a mercury thermometer would break.
Oh, yeah, the old ones.
And that liquid silver, it would just scatter like these tiny, perfect ball bearings across the floor.
Mesmerizing, wasn't it?
Totally. And my mom would carefully nudge them back together with a toothpick. And poof, one little sphere just gulps another until it's all one blob again.
Like magic.
It really felt like it, like some kind of futuristic metal.
Yeah.
That was probably my first real moment of wonder about, what stuff is actually made of.
And that wonder, that's exactly our starting point today. Because the periodic table, it isn't just a chart. It's this immense human achievement, really.
A storybook almost.
Yeah, a storybook filled with, headstrong characters, bizarre behaviors, amazing tales. So our mission here is to peel back some layers.
Get into the science, the history.
Exactly. The utility, the forensic clues it holds, even the anthropological side, how we discovered and used these things. These 100 or so elements, they make up everything, but they also reflect our own history, our ingenuity, and our mistakes too.
So we're giving you the shortcut, the important stuff, why it all matters.
That's the goal.
Okay, so let's circle back to mercury, that shimmering liquid. As I got older, learned it was toxic, the magic definitely faded into, a bit of a chill.
Understand.
But what's actually going on there, elementally speaking, to make it do that ball-bearing thing?
Well, mercury is unique because it is an element. Its atoms are, let's say, quite self-contained. They really prefer sticking only with other mercury atoms.
So they don't like mixing?
Not really. They minimize contact with anything else by pulling themselves into those perfect spheres. It reduces surface area. Most liquids just spread out, right? Mercury holds itself together. That's its elemental nature showing through.
It's amazing they have these personalities, like introverts and extroverts.
You could definitely see it that way. I mean, think about the noble gases, helium, for example. They're the ultimate pacifists, the introverts of the table.
Perfectly happy on their own.
Completely. Their electron shells are full, stable. They rarely react with anything. Helium especially shows this extreme elementness. If you cool it down to, minus 456 Fahrenheit?
Wow.
It becomes a superfluid, zero viscosity. It flows without any friction, defies gravity, climbs up walls. It's really astonishing, a perfect, ideal form in action.
But these peaceful guys, they have some really rowdy neighbors on the table, don't they?
Oh, absolutely. It's like a chemical DMZ.
A demilitarized zone.
Exactly. Right. One column over, you've got the halogens, super reactive gases. And way over on the other side, the alkali metals.
Also very reactive.
Extremely. Both groups are desperately seeking stability. Halogens need one more electron for a full outer shell. Alkali metals have one extra they're dying to get rid of.
So they're a natural fit.
The perfect match. One gives, one takes. It's all about satisfying that octet rule. Getting 8 electrons in the outer shell for maximum stability drives so much of chemistry.
Incredible. And some elements, they almost seem to enjoy playing tricks.
They do. Gallium is a fun one. It's a metal, looks like any other metal, but it melts at just 84 degrees Fahrenheit.
So like body temperature.
Exactly. You hold a chunk in your hand, and it just turns into this thick, grainy puddle, pseudo-quicksilver.
That's wild.
Yeah, the classic prank is making gallium spoons. Stir your tea, and poof, the spoon just disappears.
Okay, that's a good one. But some tricks are much darker, right? Historically speaking.
Antimony. Definitely antimony. It has this really colorful, often quite sinister past.
Like what?
Well, Nebuchadnezzar might have used an antimony compound for yellow paint in his palace. Some think it contributed to his madness. Maybe. Ancient Egyptians used it in mascara. Medieval monks got weirdly obsessed with it. They even used antimony pills as reusable laxative.
Reusable? Ew.
Yeah, don't ask. But its modern use is perhaps even scarier. Mix it with hydrofluoric acid, and you get a superacid.
That was super.
pH of minus 31. That's 100,000 billion times stronger than stomach acid. It eats glass, eats your hand. Deceptive stuff.
Yikes. Okay. And then there's bismuth, which sort of breaks the pattern.
Bismuth is a real paradox, yeah. It's a heavy metal, sits right there in the poisoner's corridor with arsenic and antimony.
But it's not poisonous.
Surprisingly benign. It's even medicinal. It's the bis in Pepto-Bismol, helps soothe ulcers.
No way.
Yes way. It completely challenges our assumptions about neat patterns on the table. Shows you there are always these unpredictable stories hidden within.
So these elements have their own stories, but they've obviously shaped our story too. Where did a lot of them first kind of come into the picture for us?
Well, there's this one place in Sweden, a little hamlet called Ytterby. Just a nondescript mine, really.
Ytterby. Sounds familiar.
It should. It's kind of an anthropological marvel because that one mine inspired the names of 7 different elements.
7 from one mine.
7, yttrium, ytterbium, terbium, erbium, then holmium, thulium, gadolinium, all named in tribute to this one spot. It really shows that intersection of human curiosity, digging around in the physical world, and the drive to find new building blocks, eventually filling out Mendeleev's table.
That's incredible. Okay, shifting gears a bit. Thinking about elements and life itself. Sci-fi loves silicon-based life.
Oh yeah, it's a classic trope. Makes us question our carbon-centric view.
But chemically, it seems like there are some pretty big problems with it.
There are major hurdles. Carbon is just so versatile. It forms 4 stable bonds, easily makes rings crucial for storing energy, and its oxide, CO2, is a gas that's vital for life as we know it, right? Respiration, circulation.
Right, easy to move around.
Exactly. Silicon can form 4 bonds, but it almost always grabs onto oxygen to make silicon dioxide, SiO2, which is right, a solid, a very stable solid. It doesn't become a gas until maybe 4,000 degrees Fahrenheit. Imagine trying to breathe sand or circulate nutrients using something that doesn't dissolve in water. Plus, silicon atoms are bulkier. They don't form those energy-rich rings easily.
So probably no silicon aliens then.
Less likely, let's say. But silicon did totally revolutionize our technology. That leads us to the whole semiconductor story.
Bell Labs, right? Post-war.
Yeah, 1945, Bell Labs. This guy, William Shockley, had a vision. Replace bulky, hot vacuum tubes with a tiny amplifier made of silicon.
The transistor.
Well, the idea of it, silicon itself was actually too brittle, too hard to purify back then. So his team, Bardeen and Brattin, they actually figured it out first using germanium.
Germanium, not silicon.
Not initially, no. Germanium was easier to work with at the time. Shockley, by the way, bit of a complex figure, brilliant scientist, but later got into some really ugly, controversial eugenics stuff.
Right, yeah. Okay, so germanium kicked it off, but silicon is what we use now.
Yeah.
How did that switch happen?
By the late 50s, computers needed tons of these transistors, and they were connecting them all by hand. Soldering wires. It was called the tyranny of numbers. Hugely expensive, prone to errors.
So, not scalable.
Not at all. Then Jack Kilby, over at Texas Instruments in 1958, had the breakthrough. He figured out how to put multiple transistors and the connections all onto one single piece, a chip of silicon.
Integrated circuit.
That's the one. It solved the tyranny of numbers. Suddenly, you could pack immense computing power into tiny spaces. That invention basically paved the way for, well, everything. Moon landings, the internet, the phone in your pocket.
Amazing. But elements haven't just driven innovation, they've been central to conflict too.
Oh, profoundly. They became strategic resources worth fighting for. Think World War I. The German Big Bertha cannons, these massive siege guns. They needed incredibly durable barrels to fire huge shells. The secret was adding molybdenum and tungsten to the steel.
Molly be damned.
Yeah.
Wasn't that the phrase?
That's the one, for molybdenum. There was even this remote molybdenum mine up in the Rockies that became the site of a really brutal, high-altitude battle over its control. And in World War II, tungsten was the it metal. A whole Wolfram War was fought diplomatically and covertly over controlling Portuguese tungsten supplies.
And sometimes the connection's even darker, like with nitrogen. Fritz Haber?
Haber is a chilling story. A brilliant chemist who won a Nobel for synthesizing ammonia from air essential for fertilizer, feeding millions.
The Haber-Bosch process.
Right. But he twisted that genius into warfare. He figured out how to use nitrogen for cheap, powerful explosives, and then he personally oversaw the first major chlorine gas attack at Ypres in WWI.
Horrific.
Truly. He even developed Haber's rule, a cold equation calculating how much gas kills how many people over time, and later a gas derived from his work, Zyklon B, that's what Nazis used in the death camps, killed millions, including some of Haber's own relatives who hadn't fled Germany. A real Faustian bargain.
And this link between elements and conflict, it's sadly not just history, is it?
No, it continues. Look at coltan, the mineral ore that contains niobium and tantalum.
Essential for phones, capacitors.
Exactly. Demand for cell phones in the late 90s, early 2000s skyrocketed demand for coltan, mostly mined in the Democratic Republic of Congo.
And that fueled the war there.
Fueled horrific violence, atrocities. Farmers left their fields, militias took control, poaching guerrillas for food became common, just brutal exploitation. And while manufacturers tried to shift supply chains, the conflict never really stopped. Now, tin needed for lead-free solder and electronics is also tangled up in funding conflict in the same region.
It's heavy stuff.
Yeah.
Beyond war and tech, elements mess with our bodies too,
Mm.
sometimes in really deceptive ways. Our senses aren't always reliable guides, are they?
Not at all, especially with elements. Take beryllium element number 4. What does it taste like?
Metallic, bitter.
Sweet. Like sugar.
Seriously, beryllium tastes sweet.
Yep. You'd think evolution would give us great detectors for quick energy, like sugar. But nope, beryllium, this toxic metal, trips the same taste receptors.
That seems like a terrible design flaw.
It is. And dangerous. Beryllium dust is highly toxic if inhaled. Enrico Fermi, the famous physicist, he died from lung inflammation, pneumonitis, very likely caused by inhaling beryllium powder during his nuclear work. Our sense of taste can be fatally fooled.
Wow. And sometimes the deception is even more subtle, even with something like breathing.
It's quite sobering, yeah. Nitrogen gas. It makes up most of the air we breathe, normally harmless. But pure nitrogen can kill you without you even noticing.
Oh.
Because our bodies don't actually detect a lack of oxygen. We detect a buildup of carbon dioxide, CO2.
Okay.
So if you walk into a room filled with nitrogen, you keep breathing out CO2. Your brain thinks everything's fine. No panic, no gasping. You just feel maybe a bit lightheaded. Then you blissfully pass out from oxygen deprivation. Miners, astronauts. It's a known hazard, an evolutionary kludge, you could call it.
Nitrogen kills with kindness. That's unsettling.
It is. The initial casualties on the Space Shuttle Columbia, for instance, likely didn't suffer. They just blacked out in a nitrogen haze as the cabin lost pressure.
But elements aren't all bad news for the body.
Right.
Some are actually medicinal.
Absolutely. Think copper and silver. They have what's called the oligodynamic effect.
Oligodynamic.
Means they kill microbes just by being there. They're self-sterilizing. That's why you see brass doorknobs, copper pipes in hospitals sometimes.
Ah, right. Public health.
Exactly. Copper ions mess with microbe metabolism, but our own cells are generally fine. It can help control things like Legionnaire's disease in water systems.
But silver. There's a catch with silver, isn't there? The blue man.
Ah, yes, Argeria. The downside. If you ingest too much silver, usually colloidal silver remedies.
Which people still sell.
They do. It can build up in your tissues and react with sunlight, turning your skin this permanent, ghastly, grayish blue. Zombie Smurf blue, the book calls it.
Like the blue man from old freak shows or that politician Stan Jones.
Exactly. Not fatal, thankfully, but definitely permanent, a very visible side effect.
And on a completely different note, there's lithium, an element that can actually stabilize the mind.
Lithium is fascinating. It's just a simple salt, but it has profound effects for people with bipolar disorder, like the poet Robert Lowell.
He found it really helped him.
Immensely. He famously said something like, "It's terrible to think that all I've suffered might have arisen from the lack of a little salt in my brain." It brought him stability.
But it raises that question, doesn't it? Does curing something like that also dampen the creative fire, the highs that sometimes fuel art?
That's the ongoing debate. Trading intense peaks and valleys for a more level, maybe more prosaic existence. There's no easy answer.
That connection between mind and matter, belief and evidence. It brings us to pathological science.
Right, where the desire for a result kind of overrides the actual data. The cold fusion saga with Pons and Fleischmann in 1989 is the textbook case.
Fusion at room temperature. Clean energy forever.
The promise was huge. They claimed they'd achieved nuclear fusion in a jar, essentially. The world went wild for a bit.
But it wasn't real.
Overwhelmingly, no. Other labs couldn't replicate it consistently. Their measurements were likely flawed. But the allure, the need for it to be true, was so strong. The community became almost like a besieged cult, ignoring contradictory evidence. It didn't help that palladium, one of the metals they used, does have this weird ability to soak up huge amounts of hydrogen.
So there's a kernel of weirdness there.
A kernel of weirdness, yes, but not fusion.
And this kind of pathological belief isn't just in physics, right? Megalodon.
The giant prehistoric shark.
Yeah.
Yeah, the belief that Megalodon might still be out there is another example. It partly stemmed from misinterpreting manganese coatings on some fossil teeth.
Thinking they were younger than they were.
Exactly. Scientists showed the manganese buildup could happen much faster than initially thought, meaning the teeth were still millions of years old. But the idea took hold. Like with Area 51 or UFOs, sometimes doubt from the establishment just makes believers dig in harder.
They want to believe in the extraordinary.
Precisely. They point to things like the coelacanth, the living fossil fish, as proof that science can be wrong about extinctions. It taps into that desire for mystery, for giants still lurking in the deep.
Okay, let's zoom way out. From our bodies and beliefs to the cosmos. Where do all these elements actually come from in the first place?
Stars. Stars are the universe's element factories.
Forging elements inside.
Through nuclear fusion, yeah. Stellar nucleosynthesis. Stars like our sun fuse hydrogen into helium. That's the basic step.
But what about heavier stuff? Iron, gold, uranium?
For those, you need much more extreme conditions. Only really massive stars, much bigger than our sun, can create elements heavier than iron, and they only do it right at the end of their lives in the incredible explosion of a supernova.
So they create them and then blast them out.
Exactly. Every possible combination of element and isotope gets cooked up and then spewed across the cosmos in this particle blizzard. That's where the raw materials for planets and eventually us come from. You scoop up soil, you're holding bits of exploded stars.
Mind-blowing.
Yeah.
And within that cosmic mix, some elements are just incredibly rare, almost non-existent here on Earth.
Oh, yeah. Acetine and francium are the ultimate examples. Acetine, element 85. Best guess is there's maybe 1 ounce of it in the entire Earth's crust at any given moment.
1 ounce in the whole planet.
It's like losing a specific Buick, named Acetine, in a parking garage that covers the whole continent, multiple levels deep. Francium is slightly more common, maybe 20 or 30 ounces total.
But still basically nothing, and they don't stick around.
Not at all. They're incredibly unstable. Half of any francium sample decays in about 20 minutes. It's basically useless except for detecting its fleeting existence. Too fragile.
But wait, uranium is heavy too, and it sticks around for billions of years. Why are some heavy elements stable and others fall apart instantly?
That comes down to magic numbers.
Magic numbers.
Yeah.
In physics.
In nuclear physics, yes. Maria Guppert-Mayer won a Nobel for figuring this out. Just like electrons fill shells around the atom, protons and neutrons fill shells inside the nucleus. And certain numbers of protons or neutrons, 2, 8, 20, 28, 50, 82, 126, make the nucleus exceptionally stable.
Like the noble gases for electrons.
Exactly analogous. Oxygen with 8 protons and 8 neutrons is doubly magic. Super stable. Even heavy elements like lead, 82 protons, or uranium benefit from having numbers close to these magic configurations, giving them relative stability despite their size.
And this leads to the idea of finding new, stable, super heavy elements, the island of stability.
That's the theoretical prediction, yes. That beyond the known, very unstable heavy elements, there might be an island where elements around, say, element 114 or higher, with the right magic numbers of neutrons, could be surprisingly long-lived. Maybe minutes, days, even years instead of microseconds.
And they might have weird properties.
Potentially very novel properties, maybe acting like metallic noble gases, things we can't easily predict. It's a huge area of research, trying to synthesize and detect these fleeting giants.
Is there a theoretical limit, though? Can elements just get heavier forever?
Well, theory suggests things get really weird around element 137, sometimes nicknamed feynmanium.
After Richard Feynman?
Right, because calculations combining relativity and quantum mechanics predict that for an atom that heavy, the innermost electrons would have to be moving faster than the speed of light to stay in orbit.
Which is impossible.
According to relativity, yes. So that's a point where our current understanding seems to break down. The irresistible force of quantum mechanics meets the immovable object of relativity. We don't really know what happens beyond that.
Okay, let's come back to Earth for a second. Measuring things. We've redefined almost all our units based on constants, right? Except one.
The kilogram. Until very recently, it was the odd one out. Still defined by a physical object. The International Prototype Kilogram, or Le Grand K.
A lump of metal in a vault in Paris.
A specific cylinder of platinum iridium kept under multiple bell jars. Scientists treated it with almost phobic care. Never touched special cleaning protocols.
But it was losing weight.
Alarmingly, yes. Compared to its identical copies stored around the world, checks in the 1990s showed the main kilogram seemed to be mysteriously losing mass. Tiny amounts, micrograms, Maybe the weight of a fingerprint, but
A
still.
huge scientific embarrassment if your fundamental standard isn't stable.
Exactly. It drove the decades-long push to finally redefine the kilogram based on a fundamental constant, Planck's constant, making it universally reproducible. You can now, in theory, email the definition of a kilogram.
From physical objects to fundamental constants. That feels like a theme. Yeah. And speaking of shifts in science, the Manhattan Project brought a whole new method, didn't it? The Monte Carlo method.
It really did. They were trying to figure out neutron diffusion in the first atomic bombs. How likely is a neutron to bounce off this nucleus, cause fission in that one, billions upon billions of interactions?
Too complex to calculate directly.
Way too complex for the math of the time. And experiments with plutonium were incredibly dangerous and expensive. So Stanislaw Ulam and John von Neumann came up with this statistical approach.
Monte Carlo, like the casino.
Precisely, because it relied on randomness. Instead of exact equations, they said, let's just simulate thousands of individual neutron paths using random numbers to decide what happens at each step. They had rooms full of people, mostly women, working as human computers, literally rolling dice or using random number tables to track these hypothetical neutrons.
Plug and chug statistics.
Basically, it was seen as an expedient, almost temporary fix, but it worked brilliantly. And that method, simulating complex systems using random sampling, is now fundamental to almost every field of science. Chemistry, finance, weather forecasting, indispensable.
Amazing how a wartime short bit became so central. Okay, final big question, back to the cosmos. Enrico Fermi, after calculating the odds for life, asked that question.
Where is everybody? The Fermi paradox.
Right. Given the age and size of the universe, billions of stars, billions of years, shouldn't we have seen signs of other intelligent life by now?
It's a profound question, and there are many proposed answers. But one ties back to the fundamental nature of the elements and the laws governing them.
How so?
What if the fundamental constants of nature, things like the strength of gravity or the fine structure constant alpha, which governs electromagnetism, aren't actually constant?
They could change. Over time or space?
There's some disputed astronomical evidence suggesting alpha might have been slightly different in the distant past or in faraway galaxies. If these constants can vary, even slightly, then the conditions needed for stable atoms, for stars to form correctly, for chemistry complex enough for life to arise, those conditions might only exist in very specific, maybe rare, unremarkable pockets of space.
Like ours.
Like ours. Maybe the laws of physics themselves are only just right for life in certain cosmic neighborhoods or epochs. It would mean life isn't inevitable everywhere, but incredibly contingent on these fundamental values being exactly what they are here and now.
So the answer to where is everybody might be.
Yeah.
They can't exist anywhere else or anywhere else yet.
It's one possible and quite deep, unsettling resolution to the paradox. Our existence might be even more precarious and special than we thought. Hashtag outro.
Wow. Okay, so from mercury spills on the floor to the fundamental constants of the universe, we've covered a lot of ground.
We really have.
We've seen elements with quirky personalities like gallium, dark histories like antimony, elements shaping war with molybdenum and conflict minerals like coltan, elements tricking our senses like beryllium, healing minds like lithium.
And elements forged in stars, defying physics at the extremes, forcing us to rethink even how we measure reality with the kilogram or how we do science with Monte Carlo.
It really drives home that the periodic table isn't just some static chart. It's this incredible living saga. Discovery, ingenuity, human error.
Yeah.
It's all in there.
Absolutely. It's written in bubbles and bombs, in money and poison, in medicine, and in the very fabric of the cosmos itself. It influences everything.
We really hope this deep dive has given you, our listeners, a new way to look at the elements that make up your world and yourselves. Science isn't separate from human stories. It's woven right through them.
Yeah.
Sometimes beautiful, sometimes, unsettling.
But always fascinating.
Definitely. So here's a final thought to leave you with. Considering how much these elements can deceive us, shape us, and challenge our deepest understanding of reality, what other secrets, what other stories might still be hiding in that table, just waiting for us to uncover them?